So this is a follow-on video from my previous video on Taylor's theorem. In that previous video we proved the theorem and then applied it to the Maclaurin expansion for the exponential function. In this video we're going to have another example of applying it to prove convergence of a infinite power series. This time we're going to do cos of x, so we'll do the Maclaurin expansion for cos of x. So I'm hoping everyone watching this video will already be familiar with the Maclaurin expansion for cos of x. So it is 1 minus x squared over 2 plus x to the power of 4 over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial, and this pattern continues where you just have the even powers and you have the sign alternating between positive and negative. So if we wanted to write that in a shorter notation, it would be sum from I is equal to 0 to infinity, and then we want x to the power of 2i. So that will get us, when I is 0, it will get us this one. When I is 1, it will give us this one. When I is 2, it will give us this one, 3, etc. And then it's going to be over the corresponding factorial, so 2i factorial, and then we just need to put in something to make the minuses right. So we're going to have minus 1, and then it's going to alternate. So it's going to be to the power of I, and this corresponds to 1, so that will give us a negative. This corresponds to 2, so this will give us a positive. So it looks as though it's perfect. So that looks perfect. So that's a nice shorthand for this infinite power series. So our goal is to prove that this thing truly does converge, and it converges in fact the entire real line, which is quite incredible when you consider how strange a function cos of x is. You know, these sinusoidal waves. So I'll draw that, and it's a very bad drawing, obviously. It should be, you know, this length should be the same as this and this, but it's the basic idea, and this goes on forever. And this is a very different function to, you know, polynomials, which, if it's a positive polynomial, go off to infinity on either side, and if it's a negative polynomial, go down to negative infinity on either side. So it's quite incredible that this infinite series of polynomials becomes this, or converges to this. And we're going to prove that with Taylor's theorem, but before we do that, if you haven't actually seen the graphic evidence of this before, I highly suggest that you do that. So you can go on to something called Desmos. So if you type into Google, I almost spelt that wrong. If you type into Google Desmos and then graph, and then the first entry that you get up is a link to this website, and this is a website that allows you to put in formulae for functions, function rules, and it will generate a graph. So for instance, you can put in cos of x and you'll get the beautiful, a much better picture of cos of x than I've drawn here. And then you can put in another function to plot alongside your first one. So you can plot two functions on this graph. And then the second one that you can put in the Taylor polynomials, and you can put in progressively bigger and bigger Taylor polynomials. So you might start with just this bit, and then you'll go to this bit, and then you'll go to this bit, and this bit, etc. And what you can see is how, with each of the additional terms that you add on, how it becomes a better and better approximation. And it's truly magical. If you've never seen that before, I highly recommend you go to this website and you do it for yourself so you can watch how this truly does become a better and better approximation. So that's some sort of like actual visual evidence. Of course, that's not a proof, but it's a very compelling visual argument that this thing truly does work. So let's move on to the proof then. So we want to prove that for all real numbers, this series converges to this. So we will take a general value within the real line. So we'll take a general x here, and we want to show that for that general x, this series converges to cosine of that value of x. So we're imagining x is now fixed. As far as this infinite series is concerned, x is now fixed. And we just want to show that this infinite series with that x value inputted in here converges to cos of that value. And then because we kept everything general, we didn't make any other assumptions about this x other than that it was in the real line, our argument will then hold true for all the elements of the real line. So we'll have proven pointwise convergence of this infinite power series to cos of x. So the infinite sum really means the limit of the sequence of partial sums. So we want to show that cos of x is equal to the limit as n approaches infinity of this sequence of partial sums, which is given by sum from I is equal to 0 to n of x to the power of 2i over 2i factorial minus 1 to the power of I. So this is our aim. Now, we can manipulate this. So we're kind of doing a backwards proof here. We're starting with our aim and we're seeing how we're going to be able to prove it. So we can manipulate this because this is just a constant as far as this limit is concerned. Remember, we're imagining we fixed our x, so this is just some value, whatever cos of that value of x is equal to. So we can bring this onto this side to get cos of x minus this is equal to 0, and then we can pull this inside the limit using the algebra of limits. So this will become the limit as n approaches infinity of cos of x minus the sum from I is equal to 0 to n x to the power of 2i over 2i factorial minus 1 to the power of I. And we need that limit to equal 0. So if we can show that this is true, then we'll have that this is true, and therefore we'll have that this is true. So this is good. We like this because this is something that we can replace with a more simple expression using Taylor's theorem. So now's the part to remind ourselves of what Taylor's theorem says. So just a little aside here. So we have f of x, and we can write it approximately. So I'll turn this into approximate equals using a Taylor polynomial. So here is the nth Taylor polynomial. And we know that this will be correct at least one point, which is the point x is equal to a, which is the point where the Taylor polynomial is centered around. Now, of course, this was a Maclaurin expansion, so helpfully a is equal to 0 here. The Taylor polynomial, however, might be wrong everywhere else. What Taylor's theorem says is that it's possible to add on one additional term onto this Taylor polynomial that will make it correct at a point of your choosing. So if you now choose a point, which we'll call x0, and you want to add on a term here that makes this approximation correct also at that point x is equal to x0, it's going to keep it right at x is equal to a, but it's also going to make it right at x is equal to x0, then that term that you need to add on is of this form: the n plus 1th derivative evaluated at some value which we give the fancy, or at least I'm going to give the fancy Greek letter chi, and then we'll have x minus a power of n plus 1 over n plus 1 factorial. And importantly, this chi, there's an important fact about it, which is that it will lie in between a and x0. So if we draw, oh gosh, I don't know quite how I made it jump like that. So if we draw a little picture here, so we've got some function, which is the one we're trying to approximate, and we have centered the Taylor polynomial around a, so this is f of x here. And now we've got some point x0, and we want to make sure that our approximation is correct at that value. So you can take this polynomial and just add on this term, and there's some magic value that you've got to stick in here. So if you just put any old value in here, it won't make it work in general. But there is a magic value that you need to put in here, and that magic value is going to be the n plus 1th derivative of your function evaluated at some value that's in between these two. So the chi is going to be in between a and x0, and if x0 was on this side of a, then it would be in between them still. So that's really what Taylor's theorem tells you. It tells you that there exists a chi, sorry, that's not a chi, that's a xi, the Greek letter xi, not chi. There exists a xi in between a and your value x0, such that when you take its n plus 1th derivative, it is the magic value that needs to be put in here to make this approximation not only right at a, but also right at x0. So now, if you put in x0 in here, evaluate this function at x0, so put in x0 here and x0 here, this will actually be the value f of x0. So that xi exists. That is what Taylor's theorem tells you. Now, this is useful to us because over here, we've actually got something that is a function evaluated at some specific value x. So x is actually going to take the place of our x0 here, minus the 2nth Taylor polynomial. Remember that when you go up to n here, you've actually got up to the 2nth term of the Taylor polynomial. It's just that loads of the terms have 0 coefficients because the derivative was 0. So subtract this Taylor polynomial, this 2nth Taylor polynomial, again evaluated at a specific value x, which is our equivalent of x0. So in this formula here, you've effectively evaluated it at x0, which turns it not into an approximately equal to, but into an actual equals. And then you've just taken this thing to this side, so that you've got f of x0 minus pn of x0. And now what Taylor's theorem tells us is that the value of that is going to equal x0. Now our a is 0 here, so it's going to be just x to the power of the 2n plus 1 over 2n plus 1 factorial, and then with this magic coefficient that is going to be the f2n plus 1 derivative of our function cos of x, evaluated at some xi that is in between 0 and x. So what we can now do is say that this is going to be equal to, this entire thing, all of this, is equal to, and I want to make sure to get this right, so it's going to be the next derivative along. So remember, this Taylor polynomial goes up to the 2nth term, so it's going to be the 2n plus 1th derivative, and that's of our function cos of x, evaluated at some magic value xi that is in between 0 and x. So on our picture, it's somewhere in here, and we don't know what that value is, but we know it's somewhere in between 0 and x, times our value x, which is a fixed constant, remember, to the power now of the next power along. So we've got up to x to the power of 2n, so it'll be x to the 2n plus 1, and then all divided by the relevant factorial, which is going to be 2n plus 1 factorial. So this limit that we're trying to prove is equal to 0 actually just becomes this. So as long as we can prove this thing is equal to 0, then we will have that this is equal to 0, and so on backwards. We'll have what we need to show. Now this looks a little bit problematic initially because we don't actually know what this xi is equal to. All we know at the moment is that it's within the interval 0 to x, where we're assuming here that x is greater than 0. If x was less than 0, it would be the other way around. It would be the interval x to 0. But on our picture, x has always been nicely on the right of 0 here. So this is the relevant interval to our picture that we've had all along. However, it's not a problem that we don't know what xi is equal to, and the reason is, look at this limit that we've actually got here. Now x is some constant, and yes, as the sequence progresses, each time you go up to the next term along, you are increasing the power here, so you're actually multiplying by x squared every time you go up from one term of the sequence to the next term of the sequence. Now, x could be 1,000, it could be 1,000,000, so you could be multiplying by an absolutely huge number. So it looks as though this term might be going out of control. Of course, it could be a tiny little value. It could be modulus less than 1, in which case it would actually be shrinking down. But in general, that's not going to be the case. So it could, in general, be blowing up. However, this is the saving grace, this factorial on the bottom here. This is getting bigger and bigger and bigger, and the size of these numbers that you are dividing through by are unbounded. You know, they're going to get out of controlly big, and they're at some point going to dominate whatever this is equal to. So if you think about the terms of, and we'll use just a simpler example, if we had a sequence like x to the n over n factorial, and you can imagine for some x maybe that's a big number like 1,000, if you have the first few terms, it's going to be like 1,000 over 1, and then the next term is going to be 1,000 squared over 2 factorial, and then the next term is going to be 1,000 cubed over 3 factorial, so 3 times 2. So yes, these things on the top are going to get very big, but then way down the line, you know, once you're past 1,000, think when you're up to like the 1,000,000th term, yes, you'll have 1,000 to the power of 1,000,000. Let me just get some more space. Oops. So yes, you'll have 1,000 to the power of 1,000,000, but then on the bottom here, you're now going to have 1,000,000 factorial, and then when you go up to the next term along, on the numerator, you're going to multiply by 1,000, and then on that denominator, you're going to be multiplying everything by 1,000,001. So actually, the amount you're multiplying by is soon going to be much greater on the denominator than it is on the numerator. The factorial will always dominate this exponential term that you've got up here at some point, because this x is fixed, so you're only multiplying by that x, whereas the amount that you're multiplying in the factorial is just getting bigger and bigger and bigger, and at some point will dominate. So, you know, at this point you'll be multiplying in effect by some 1 over 1,000, and then onwards it will just be getting smaller and smaller. So it's going to vanish this thing away. So as long as this is bounded and isn't going out of controlly big to compensate for how out of controlly big the thing in the denominator is getting, it looks as though we are going to have our wish that this thing's limit is going to equal 0. And indeed, this thing doesn't get out of control. This thing we can bound very easily. So if we think now about differentiating our function cos, so cos has a beautiful pattern to its derivatives. So cos of x, differentiate it, you get minus sine of x, differentiate again, you get back to cos, you've got minus cos, differentiate again, and you'll get sine of x. So differentiating cos gives minus sine, so the minuses cancel, and then differentiating sine again, you get cos of x, and then it just goes round and round in this cycle, so it cycles every 4 derivatives. Now, we are then, so this 2n plus 1th derivative, it will be sine cos, negative sine, negative cos. It'll be one of these 4 here, and it's going to be evaluated at some xi, and we don't know what that xi is equal to, but it doesn't matter, because all of these functions, so if we think about cos of x, it looks like that. If we think about negative sine of x, it looks like that. If you think about negative cos of x, it's just the mirror image of that one on the top, so it looks like that. If you think about sine of x, it looks like that. The point is, all the values, no matter what value you put in within the real line, the value is always going to come out between -1 and 1. So this value for f2n plus 1 of xi, even though we don't know what xi is and we haven't thought about what this derivative, which specific one it is equal to, I can immediately say that it's bounded above by 1 and bounded below by -1. The biggest it can be is 1, and the smallest it can be is -1. So writing that out here, fn plus 1 of xi is less than or equal to 1 and greater than or equal to -1. So now what we can do is we can work this limit out using the squeeze theorem. We can write that it's all of these terms are going to be less than or equal to something and greater than or equal to something else, and then both of those things, their limit as n approaches infinity is going to be 0, and therefore the thing in the middle is sandwiched in to 0 as well. So we're going to write down a nice squeeze theorem inequality for this. There is one final little complication that we're going to take care of with this inequality, which is that if x is a positive value, then x to the power of 2n plus 1 is always going to be a positive value, whereas if it's a negative value, this is actually going to always be a negative value because it's 2n plus 1, so it's therefore an odd power, so it will be a negative value. So this sequence is going to be, well, ignoring this bit, this sequence would be all positive terms if x is greater than 0, whereas it would be all negative terms if x was less than 0. Of course, this thing means that it might be flipping signs in reality, but we're going to take care of that complication in this inequality as well. So let me show you what I've got in mind. So my claim is that fm plus 1 xi x to the power of 2m plus 1 over 2m plus 1 factorial for all little n is an element of the natural numbers. My claim is that this is going to be less than or equal to, and then I'm going to put in place of this 1, and then I'm going to put in mod of x, so we're going to force it to be positive, to the power of 2n plus 1. That gets rid of the complication of this potentially being a negative number. If I just put x in there, then this would be complicated by that, potentially. And then over 2n plus 1 factorial. So that's a nice positive number there. And then on the other side, it's going to be greater than or equal to the negative version. So we're going to have now minus 1 for this. And then we'll again just put in mod of x to the power of 2n plus 1. Again, if we didn't put that mod there, this could potentially be negative and ruin this. It could, because then the negatives would cancel and then it would be garbage, just an inequality. So we need that mod there. And then again divided by 2n plus 1 factorial, which is a positive value. So this is a negative number of size, this, and this is a positive number of size, this. And this thing, no matter what x value, and no matter what this is between negative 1 and 1, this thing's always going to lie in between those two, and I hope you agree with me on that. And now we can apply the squeeze theorem, because the limit of this as n approaches infinity and the limit of this as n approaches infinity is going to be 0 by the argument that I've given here, that this factorial in the bottom at some point is going to grow a lot faster than this. This is growing at a continuous rate. Every time you go up to the next term, you're multiplying by mod of x squared. And yes, mod of x might be huge, so initially this thing might dominate the factorial, but at some point this will overtake and completely dominate it out, because it's going off to infinity, so that each time you're going to be multiplying by 1 over something that's getting huge. So it will at some point dominate that. So this thing's limit is 0, this thing's limit is 0, and as this is always in between those, this thing's limit is 0. So we've done it then. So we've shown that this thing's limit is going to be equal to 0, and therefore this limit is equal to 0, and therefore truly that for this value x, this series does converge to this. And then because x was general, our argument holds for all x as a real number, and therefore by universal introduction, we can say for all x as an element of the real line that this does hold true. Cos of x is equal to this. So we'll end there. Thank you for watching.